Uh, Now it's recording. Welcome back to the class. I'm sorry about the vacation last week. I'm away for uh, two classes, so we'll do a makeup class. Now let me finish up the last section of the x86 assembly, part 3 of our x86, mostly about what happened when you have function call. So function call are actually really common thing, right? When you write a program, and especially a good program, a good modularized program contains multiple function calls. So how does assembly handle that? Because at the end of the day, if assembly doesn't know how to handle that, you cannot run, right? A quick announcement: we will have a makeup class. The first makeup class on July 6th, Wednesday, 10 a.m. to noon. This will be a material not on the exam, but hopefully it's there to motivate you for the topics in computer system. The second makeup class will be on Monday. Basically, review session 2 to 4 come with questions. We will record it. There'll be another review session on Thursday of that week, right? I double check on the Sky Plus. It seems like Thursday we don't have to cancel the class, even though it's a holiday. I don't know what's the system, but basically we have class on Thursday, and I kind of forgot what I want to say. We have class on Thursday, and we'll do a review session. The second review session. The first review session, we focus on the uh, the third module. When we talk about caching, we talk about virtual memory. There is so many confusion coming from this topic alone, but it's so important to many things you're gonna go and do in the future, especially caching. It's actually matter for performance, right? It's done everywhere inside data center, inside database system. It's done in most good and high performance web application. It's actually done in multiple level of the computer, including inside your own CPU, right? So we'll learn from that. We'll learn from how this can be automatically done inside your hardware. When you buy a CPU that's done for you, it's already being designed and it actually works really well. But before we jump there, let's do a quick recap because there's a 1 week gap here, right? So last 2 weeks ago, we talked about the jump instruction, right? Jump with the destination. Destination is basically the address of the code you want to jump to. This is similar to go to command in C, which I just showed here, right? In C code, you can say go to like this, and you actually jump to the label. You just plug in, right? And you can add label in C by using the label name with a colon. It would basically annotate that line of the code with the label thing. Now you can do go to loop, right? So you can implement a do while loop using go to. Basically, the loop body comes in, then you do the if else, and then you go to, right? And you can also use the same idea and use it for for loop because it's basically you then initialize things, right? Like I equals 0, and then you check if the condition is true or not. Then you do the loop body, and then you update, and then you go back to the condition check again, back to the loop body. So you keep doing the go-to version of this. You can also then replace the for loop with a while loop, right? And it's actually the same thought process. So in summary, if you want to look at control instruction, the reason why they call control instruction is because it control where you run, how you run the program. Most of the time, your program would run line by line by line, right? Yes, the in class this today seems fun. It's fun. There are some assumptions that are made that are different from what I'm going to give the lecture on about the input into the function call. So we'll specify that later once we talk about in-class material. All right, and then I'm gonna I am going to edit the assignment with that explanation as well on where's my first input and where's my second input. So you can have C control instruction like if else, do while, or while loop or for loop, and have the assembly, right, control instruction like conditional jump, conditional move, indirect jump, which we'll talk in a bit. And the compiler is responsible for doing all this code generation for you. Basically, look at your code in C, in Java, and Python, and magically you get assembly, right? That magic is science. There's actually a lot of science going behind it, and they're still being invented even now, right? How to make sure your code run even faster and faster and faster with new hardware that comes out, and hopefully everything you do will get faster, which is an awesome goal, right? So have you used switch case in C at all? How many people use switch case in C? Anyone or not yet? All right, so for those of you who used in Java before, the way switch case work in C is the same. So I'm gonna show an example, right? So in this example, let's go through this together. What's the first line here? So I'm gonna label this line number 1. This is line number 2. Line number 3. This is setup line number 4, number 5, number 6, number 7, number 8, and number 9. So from this line, what does line number 1 do? Basic C. All right. Just look at the code and you should be able to tell what exactly is that. Yeah, define the function. It's a function signature, right? It's the name of the function with the inputs, and the inputs are X and Y and Z. Line number 2 is say W equals 1. Any question about line number 2? Let's go to line number 3 because that's line number 2 is obvious. Line number 3 is where you can use a switch case. The way you use it is first you say switch, and then in parentheses you put in a variable. In this case, it's X. What it does is it checks the value of X. Basically, over here, it checks the value of X. And then you will notice that there are multiple cases here. There are multiple cases here, right? Case 1, case 2, case 3, case 5, case 6, and default. So if I would just ask you to make a guess, when will I do things in case 1? When am I going to do things in case 1? Just make a guess from hopefully something that looks obvious here. Why and when would I run exactly, right? If X equal 1, you do inside, whatever is inside case 1. So in this case, right, if X is 1, you will do W equals Y multiplied by C. And then the next line is break. What break do in the switch case is it stopped running. When you see a break, you then jump until the end of the switch case. So if X equals 1, you do W equals Y multiplied by C, and that's all. You jump out of the switch and you're done with the switch statement. Now, if X equals 2, what should we do with W? When X equal 2. Set W to be Y over Z. And is there a break here? Is there a break? There's no break, which means that this is a case we call fall through. Fall through means we'll keep running. So what's the next line that we see? It would then go to case 3, right? It basically keep running. W equals Y over C. Then keep running. W equals W plus C. So in this case, and then you break, right? So in this case, if X equal 2, what would happen is first you would do W equals Y over C. Then W equals W plus C. which ultimately will do W equals Y over C plus C, right? If x equal 3, what you would do is basically W equals W plus C. You'll see the difference now, right? If x equals 2, you run 2 lines. If x equals 3, you jump into W equals W plus C, and then you're done. That's called fall through. No case for, a great observation, no case for. So if x equals 4, what should it do? It would go to default. Basically, if x doesn't match to anything with less, go to default. The thing is, if I don't have the default here, is it okay to not have the default? Can I erase this line? Can I just simply take out the default? The answer is yes. If that's the case and x equals 4, do nothing. Then the switch won't do a single thing, yes. Basically, if there's no default and it doesn't match to any of the case, then do nothing. Now you see case 5 and 6, right? So in that case, if x is 5 or 6, then it would do W equals W minus C, whatever the next line come in, right? So that's how switch case work. You can have fall through, right? You can have multiple level, like case 5 and 6 right here. And you can have the missing case that you just observe, right? Then you would go to default. If there's no default, do nothing. Now, hopefully this part is clear. Now let me ask this question. If I have to convert this to assembly, what would happen? How many if else are actually in here? How many jumping that you have to do in here? Uh, 1, 2, 3, yes, 5 or 6, right? Basically, the key things here is when I'm on this line. So let's say I'm on this line, switch X, right? This line. How many possible location I can jump to? How many possible different location I can jump to? 5, right? You can jump to 5 different locations, 5 different lines. But for my jump instruction, can I have 5 different inputs depending on the condition of X? No, right? So the way you implement this in assembly, we can do something called jump table. We'll now look at how this can be done. All right. Here again with the switch case, right? There has to be the setup. When you want to implement a jump table, one thing you can do is to set something up first, right? From this code, right? The setup is what? Well, you initialize W and at the end you return, right? At the end you return. On our setup code, some quick note, W is not initialized. We'll do something with it later. There'll be a full assembly code that explain everything. Now let's assume that X is in RDI, Y is in RSI, C is in RDX, and return value is in RAX. All right. How many different value would take default? So my first question is, how many different value would take default in this case? Let's say X is between 0 to 8, how many different value would take the default? If X is 0, you go to default, right? If x is 4, you go to default. If x is 7, 8, 9, 10, anything greater than 8, go to default. Quite a lot, right? Quite a lot. So the first thing we can do is, if I go to default, what is this? You always jump, right? So if x is greater than 6, these all go to default, right? If x is greater than 6, we always go to default because that's what our case cover, right? So the first thing we do in a setup code, what is this line? Compare 6 with RDI. I compare 6 with RDI. If jump above, if RDI is above 6, what does it mean? Where is L8 in this case? Anyone want to take a guess on what part of my C code would cover the .L8? The part that x is greater than 6. JA is jump above. So if x is greater than 6, you go to default, right? So over here, you can guess that L8 is default. With me, so for any question now, for now, before we go further and look into the actual jump table itself. Because it seems like, how many people here is confused now? Because I want to hopefully minimize that. Okay, yes, please. Thank you so much. So the first thing is CMPQ, compare the value. So now basically you do, yes, .L8 is an address. So first you compare the value between 6 and x, right? RDI is x. So you are comparing 6 and x. JA is jump above. If x is above 6, if x is above 6. So if x is greater than 6 from here, what should we do? If x is greater than 6, what should we do? Default, right? So basically over here, what we want to do is jump above, means that if we compare x and 6, and if x is greater than 6, you jump to .L8. .L8 is a label. It's a label that points to an address. An address in this case will be the line of code that represent your default, that block of code in the default. Is it more clear now? Basically, the first thing we do, you compare 6 and x, and we want to just take care of that case where if it's greater than 6, we're not going to worry about that. It's always go to default. So that's the first thing we do. If x is above 6, jump to default. It just turns out for the code we just compile, L8 is default. It's where is the address that contain that line where the default statement started. All right, is it more clear? So CMPQ is compare, you're comparing x and 6. If x is greater than 6, you want to go to default. So the next line, once you compare, you need to jump, right? And the condition of the jump in this case is you want to make sure x is above 6. If it's greater than 6, then you go to default. All right. So now let's go to the meat of the, I guess, first part of this lecture. We want to talk about indirect jump and the jump table, right? Direct jump is what we learned, right? Like this, jump to L8. Then you basically go to L8, right? You basically go to L8. What does the word indirect mean? What does the word indirect mean in English? Actually, that's a really hard thing to answer. I cannot think of a good synonym for that. It's not direct, right? So in computer science, so this is one of the really common technique. Yeah, roundabout way. This is one of the really common technique in computer science. We call this indirection. Indirections means that we don't directly go to the location. In this case, let's say you're here, right? The first place you go to is a table. A table consists of multiple rows, right? Let's imagine each row is a pointer. What does the pointer contain? An address, right? So each row will then point to a different part of your code because your code is an address. The starting point of your program is an address. Now you can go to the table, and then depending on whether you go to row 0 or row 1 or row number 2 or row number 3, you would jump to a different location of your code. Are you with me so far? So the first box can be when it's case 1, right? This is case 2. This is case 3. Case 4. There's no case 4. It can be case uh 5 and 6, and this will be default, right? From the example. Basically, each line in the table would allow you to go to a different location. This is called indirect jump. This is called indirect jump. You first jump to the table before you jump to your target location. It's a roundabout way of jumping. You go from one place in the code by first you check this table before you jump to the target location. The OS actually use this technique quite a lot when, for example, when you type something on the keyboard, the OS would use this technique to figure out, okay, what do we do when you type enter and when you type escape on the keyboard, all right? How do we do that? How do we do that? What is the structure of our table? How do I store the address? How do I store the address? If I want to store the address, how big should each line be in bytes? How big is one single address in a 64-bit machine? 8 bytes, right? In a 64-bit machine, an address is going to be 8 bytes long. So each entry in my table, because I want to store the address, so it's going to be 8 bytes long per line, right? And it would have a base address. Basically, there will be an address for my table, right? There will be an address for my table. But depending on something, I'm gonna jump to a different row of the table, right? So do you mind if I redraw the table a little bit here? On our switch case, what do we want to check based on? Like, what variable dictate where we jump to? What variable dictate where are we going to jump to in our switch case? X, right? So X come in, it would allow you to start if X is 0, right? If X is 0, you want to go to the first row. If X is 1, you want to, so this is if X equals 0, if X equal 1, if X equal 2, so on and so forth. Yeah, you heard it. Yes. My cat just opened the door and ran in and just ran out, and they're running around in my living room now. Um, So if x is 0, you want to basically jump to whatever. Yeah, I didn't fully close the door, so they just hit but the door and it opened. Um, and one of my cat knows that if I don't fully close the door, he can always headbutt it and it would open. So he do that a lot. Um, so for my jump table, if it's 0, you go to the first line. Take that away. If it's 0, you jump to the first line. If it's 1, you jump to the second line. If it's 2, you jump to the third line. All right, with me so far? With me so far? Let's say this is our table dot quad here. So let me first explain dot quad. This is basically make sure this part is 8 byte. Basically, it would make sure that this part is 8 byte, 8 byte, 8 byte, 8 byte, 8 byte. What comes after the dot quad from the code here? What comes after the dot quad? The address, right? So anyone remember what's L8? What's L8? Is our default, right? So if then the first line is what? When x is 0, you jump to the first line. That's default, right? If x is 0, you go to default. What other cases you go to default? When x is 4, you also go to default, right? When x is 1, now you go to a different line. So over here, these are the address of where you want to jump to. These are the address of where you jump to. Basically, that would be telling the location of where you want to jump, right? Now, the last step, which is the last bullet point here. This is our last step. This is the magic. This is how we can make it happen. All right. Let's see it how we can make it happen. Remember our addressing mode. This parenthesis thing. So x is RDI, right? X is RDI. So in this case, what is the dot L4 in parentheses percent RDI 8? What is that equal to? This is x. RDI is x. So what does that equal to? The base plus, yeah, use that formula, right? This is basically L4 plus x multiplied by 8. L4 plus x multiplied by 8. All right. So if x is 0, what is the result of that formula? If x is 0, L4, right? Which is here. If x is 0, you go to the first line in L4, that's dot L8. This line, right? What if x is 1? What if x is 1? It's L4 plus 8. L4 plus 8, right? So this is when x equals 0. If x is 1, you would then now see L3 instead of L8. You see L3 instead of L8. All right? If x is 5, for example, 5, if x is 5, you would then jump here. You see L7 instead of L3 or L8. Right? And the star here basically would tell you this is an indirect jump. Then you first jump to the location L4 plus x multiplied by 8. Whatever address you see there, jump there again. So this is kind of like how the jump table is structured, right? You have the switch case like this. The jump table would have multiple targets based on all your cases. The target would contain the actual code, like this is case, for example, this is case 1, this is case 2, right? This can be case, I don't know, 7, right? And these can be the default, right? For example. And depending on the value of x, the jump table would contain the target location. So from our sample code, this is our sample code, right? You will see that if x is 0, you then jump to L8, that's default. Then when x is 1, you go do L3. If it's 2, do L5. If it's not 3, do L9. If it's 5 or 6, do L7. All right. So that's how you can write an indirect jump and how you can cover the switch case, right? Which you see here, jump star L4. This is the indirect jump to our table, right? That multiple row, right? This is our jump table. And the row in the jump table would be dictated by whether x is 1 or 2 or 3 or 4. And what goes in there is the actual target, the actual target. Yes, that's the magic of the compiler again. What is the magic of the scientist and human that we write the compiler to do this for you? Imagine that, right? This is actually automated by GCC. The group of science. Oh, JA. Yeah, so for sure. JA is jump above. So it looks at the compare. This is compare. It compares 6 and RDI, in this case X, and you jump if the result is above, which in this case is X is more than 6, you jump to L8, which is default, right? So is it more clear? Basically, that's what JA is for. All right. Yeah, and yes, great question. These are all done automatically by the compiler through years and years and years of coding, research, and coding and research again. So if x is equal 1, then the formula is L4, actually L4 plus x multiplied by 8, right? If you look at this formula right here, is L4 plus 8 multiplied by x. So depending on the value of x, right, you then can jump to a different location. So I will show you the actual assembly code in a bit, right? In the next slide. So can I move on to the next slide so I can show you the jump table? That's actually, I'll show you the next slide. I'll show you the next slide and it will be hopefully much more clear. So here is the assembly code. Don't get scared yet. Don't go there. Don't go there. This is the check if x is greater than 6, and if x is greater than 6, go to default. All right, so we get rid of that. This is the x. This is the code here. Code number one that I just labeled. This is the number 1 here. All right, with me so far? Yes. This is the constant. Because we know that if x is greater than 6, it's always go to default, so we can get rid of that case. First of all, it's the easiest one. Get rid of that, right? If x is greater than 6, jump above, go to the default. If you look at this address, 400,614, 400,614, where's that? Where's 400,614? Can someone tell me what lines is that? Down, like all the way down. Right here. What does the line do? Remember our return value? is always assumed to be in EAX. It will be in EAX. So in this case, what are we returning? If you go to default, you return what? Return true, right? Now let's double check. Right, with our C code. So sorry, I don't want to move slides a lot, but for this particular example, there's no way I can make it fit. So I need to go back to our case here. Default W equals 2. All right, with me so far, default W equals 2. So we will return 2. We will return 2. All right, so that's the default you return 2. So now let's take care of the easiest one. The next line right here, you have the indirect jump to here, right? RDI is X. This is X. Where is my jump table? If you look at the code, you can tell where is the jump table. So what address should I look at? $4007F0, right? So if you somehow you can do this, like in a GDB, you can print the content at 4007F0 by doing this. This is basically a command that allows you to print 8 set of addresses, starting at 4007F0. So from our table, right, remember if x equals 0, this is if x equals 0, this is where you jump to if x equal 1, this is if x equal 2, this is if x equal 3, this is if x equal 4, this is if x equal 5, this is where you jump to if x equals 6, and what is the last thing here? Why is there some junk value? What if x is 7? Yeah, it's unassigned because we don't need it. Yes, thank you. This is unassigned. So now, if x is 0, you go to 400614. Let me go back a bit, right? Let me go back a bit. 400614. This is our default. So now I'm gonna go forward to the jump table. If x is 0, you go to default. If x is 1, what address am I jumping to? What lines? What is the address of the line I'm jumping to for the case where x equal 1? 4005F0. 4005F0. This is if x equal 1. You comes in here, you move RSI into RAX. RSI is into RAX, then you multiply RDX with RAX. So now do you mind if I go back to the code, and I need to also remember, I don't remember what's RSI. So here, now here's the code. RSI is Y. RSI is Y, all right? And here is the assembly, right? RSI is Y, you move RAX. So now in this case, right, this line is RAX equal Y, and you do what? You multiply RDX with Y, right? What is RDX? Let's go back to the code. RDX is C. So in this case, if x equals 1, you do what? You return y multiplied by c. If x equal 1, you basically do y multiplied by c, and then do return. Now, if x is equal to what line do we jump to? What lines do we jump to? If x is 2. 4005 F8, right? 4005 F8. So it's this line right here. You move RSI into RAX. So that's basically y equal RAX equal y. Then you set up to perform the division, because if you remember correctly, it's y, w equals y over c, right? Basically, this is perform a division. It performs the division by doing w equals y over c. All right, y over c. And this is a fall through. This is a fall through. It actually fall through case 3, right? It's actually fall through case 3. What is case 3? Where is case 3? Case 3 is what line? 400,602, right? That's when x equals 3, 400,602. If you look at 400,602, this is when x equals 3, right? This is when you have x equal 2. The first thing you do is, for x equal 3, you move 1 into REAX. This is w equals 1. Then you add w equals w plus c. So let me ask you this question. Why does the fall through case jump to 607, which is this line, rather than 602? Rather than 602. So let me jump to the C code for a bit. I jump to the C code for a bit. This is like a small thing that if you didn't exactly, you don't want to reset the EAX, because if you fall through, you start with W equals Y over C. But if you go to case 3, you would notice that W equals 1 in the beginning. At the beginning, W equals 1. But you notice, right, that w equals 1 is never done anywhere until that line. All right? W equals 1 is never done everywhere else until that line. So assembly, the GCC, when you compile, it figure out that, hey, you can optimize this code a little bit by doing the assign here. Only if x equals 3, you would assign w equals 1. Otherwise, you don't need to, right? For x equal 2, that's why you do w equals y over x and then jump to w equals w plus c directly. You delay initialization only happen when you need to do it. Only initialize w to be 1 only on the case you need to do that. This is another optimization done by the compiler, right? So if x is 4, you go to default. And if x is 5 and 6, you go to 4060B. So let's go there, right? Here's 4060B. Again, you assign w equals 1, and then you subtract, right? You subtract. This is w equal, I think w minus, what is RDX? I forgot, sorry, I think minus C, right? W equals w minus C. And that's it. That is how the code works, right? So let me confirm that. Oh, great question. RETQ is return. Basically, it's the process that return the function call. So it return the function call. It has some setup code that involved with how function call should be handled. Yeah, that's a great question. So it depends on how you do division. Usually in programming, in computer science in general, division is expensive. So in this case, you will see that this had to do the combination of these two instruction, right? And to be honest, I kind of forgot how the setup is done. So I need to double check the x86 manual on how to do this setup for the division. But yeah, it's basically the two things combined is how you would do y divides by c. All right. Okay. So that's it. So here's the breakdown of the switch case with the code you saw earlier, right? When case equals 1, you do the move RSI, RX. I'm gonna skip this because we just explained it on a big example earlier. It's the exact same thing. It's the exact same thing, right? This is where the case fall through. You can see first you do y divided by c, then you jump to w equals w plus c if case is 2. Otherwise, this is 3. You first initialize to 1, you do the w equals w plus c. If it's 5 or 6, you do w equals 1, followed by w equals w minus 7. No, w equals w minus c. And then if it's greater than 6, like 7, 8, and 9, you go to default, which is w equals 2. The quick technique for switch is if you have a large switch statement, you would then use a jump table. But GCC also is really smart. So when you detect something like switch X and then case 1, case 10, case, I don't know, 100, it would actually now convert to if else, if else, if else, if else for you, because otherwise your jump table would be huge. There'll be 3 entries for 1, for 10, and for 100. Everything else goes to default. That's a waste of space. So GCC would then convert to if else for you. All right, so that's the general things that happen under the hood when you compile your application. Now we'll take a quick break before we go to function calls. Let's do. Should we do like maybe 6 or 7 minutes break? We will resume at 3:18 p.m. All right, let's do a quick break, and now afterward we'll handle function call. I'll try to go. It's likely that we go until like 3:50, and we will not finish. So we'll continue about function call in the next class. All right. So let's do a break. We'll be back at 3:18. All right. Yeah. So let's resume the recording, and now let's cover function calls. All right. Here is the first thing I want to do. Set some general guideline on what happens when we have function call. Because if you think about it, function call is another jump, right? It's like if else, but you need to set more things up. You need to pass in the value and initialize certain things before you return, right? So there are more work that you have to do compared to an if else statement, right? Uh, so general things to do. First, you need to pass in the control. Again, control is code execution, right? Code execution. So the first thing you need to do is to make sure you know where to begin. What's the first line of my function call? And how do I return to the last line before I have the function call? Because when you have the function call like this, right? When you have a function call like this, do you return to line number 1 here or line number 2 here? Where do you return? What line? At what line do you return? Line number 2, right? So when you return, you're not returning at the beginning of my calling function. I am returning in the middle of that function. So that's the first thing you have to be careful about. When you return, you resume the execution of the earlier function right away. The second thing is you need to pass the data. You have x as an input into this variable, and then you return this, right? And when you return, this is in EAX, right, as we established already. But when you pass in the input, it will be in certain variable, in certain register, right? There are some rules here. Then there's other things like how do you manage the memory? Like in V10, right? I just create a space for 10 integer, right? And when you're done, you should be able to deallocate that as well, right? Uh, Again, the way you manage this, we want to say these are the choices that designed by programmer basically, and the choice make up the application binary interface or ABI. As the name suggests, interface means that it's something that we can use to talk to the machine, right? The ISA is more like a guidebook, a law from each chip that say, I can do this, I can do that, I can do this, I can do that. But if you want to look back at the code right here, right, at the code right here, how do I allocate the space for 10 integer? It's up to you. Who are you in this case? The OS, the compiler? They would work together. The OS will control the runtime. What happened when you run? The compiler will control what instruction am I using. And then the OS would make sure that I allocate the space for 10 integer safely so it run, right? And then you do deallocate upon return. And these would be all combined into the application binary interface. All right. Basically, this is a part of the OS. They will figure out how do we handle that. And in x86, the function call, they're done using a stack structure. A stack is first in, last out. Basically, when you call the function and you keep calling the function, and you return to the function that earlier that you just called, right? And the calling convention is you are passing the control, you're passing your data, and then you have to manage the local data. You expand into this. You expand into this. All right, you expand into this. Let's first look at the stack. Let's first look at the stack. A stack is an area in your memory, that manage, right? Manage in a stack discipline. What dictate the stack discipline is you can push and you can pop. You can push and pop. All right. Memory is going to be viewed as an area of bytes. Different region would have different purposes, right? There can be a area for like data for your address. There can be a region for your code. There can be a region for anything you do through malloc, right? And the x86 stack has the top and the bottom. The top would be pointed by RSP. That's the stack pointer. That's the stack pointer that manage the top of the stack. The region of the memory, again, managed in stack discipline, so you can push and you can pop. All right. RSP would contain the lowest address. So over here, the stack will grow downward. The stack grow downward. And here's the high address. This is the low address. So the stack keep going lower and lower and lower and lower. RSP, when you push things, RSP will get decremented. So over here was what happened when you run push and you want to push something to the stack. When you do that, what happened is first RSP goes down by 8 because one address is 8 bytes, right? So the first thing is RSP go down by 8. Then the value you want to push will get pushed to that new location you just created. And then you move the stack pointer. You move the stack pointer to the new location already. So you have the new stack top, the new stack top at the lowest address. What happened when you pop? So let's say you have a value at the stack pointer at the top right now. You run pop, right? When pop happened, the value got returned, and then you increment the stack pointer by 8, and that's all, right? The value actually doesn't change because you can leave it there. I already decrement the stack pointer, so the next time I push, the new value would replace the old value, right? So that's how stack work. That's how stack work. Then let's now talk about what happened when I have the function call, because it's managed in a similar fashion. It's managed in a similar fashion. The thing is, what do you need to do? So let's say I have function call, I don't know, function one, right? I have a code right here. And I have a function call right here, func2 x, y. And this is another code, right? Func2. When I call this function and I finish, I should be able to return right at that line, right? Right at this line. When I have a function call from to into function2, when I finish running function2, I need to resume execution at that line in function1. All right, with me so far. So I need to put something, I need to save something in order to make sure that when I return to the parent function, I can then resume. What should I save? What should I save to be able to tell what line is that function call? I need to save the program counter, right? What is the program counter? Anyone remember what's the program counter? Instruction pointer, what does it do? It point, yes, exactly. It point to the current line. So right before you call func2, one thing I can do, put the program counter, push it on the stack. I push it on the stack so that when I finish function2, I can pop later. I can pop and I can then return to that line. All right. So that's one thing you need to do when you have a function call. So now let's look at the code. The code is simple. The first code called mul_store, which call function mul2, right? Have x and y as an input. Mul2 do only one thing. I multiply and then I return. Then in mul_store, I just basically then return the result again, right? And now let's look at the assembly code. Here's the assembly for mul_store. This is the assembly for mul2. Assembly for mul2 is simple. I just move and multiply. I just basically multiply A and B, and then I call return, right? I call return. So that's simple. Any questions about mul2? Yeah, so mul2 basically just multiply A and B together. That's why the assembly for that is 3 lines. I first move A into RAX so I can return, and then I multiply B into A and write the result into RAX. So when I return, the result is stored in RAX. To call the function, you can use the command call queue, right? This would allow you to not just jump, but you call the function by pushing the program counter on the stack, and when you're done, return will pop the program counter. This is push program counter, then jump to function, pop the program counter, then jump to this, so that you can jump back to that line that you just called, right? So that's how the procedure call works. Basically, whenever you have the function call, you can do call queue over here. For example, you can call the function by call and put in the label, like the address of the function. Then when you're done, you just call ret. Ret would pop the return address from the stack, and you jump to that, right? And here's some more concrete example, right? From the code earlier, there's a call queue and move, right? So the first thing is I call queue, right? When I call queue, what happened is, what is my program counter? What is the next line? What's over here? What's the next line in mouse store? After I run function, like I finish mouse 2, what's the next line should I resume? 4005 what? 400549, right? So when you call this function, what is being saved? So this thing is your stack. This is your stack. So when you have call queue, you would push 549, which is exactly this line, onto the stack. Onto the stack. And then you update your program. This is your program counter. So that it say, hey, I'm gonna run this line now. 400550. Because that's the line, that's the function call that you want to go to, right? But this is okay. This is okay because now I have these already saved, right? Save program counter is on the stack already. So that when I finish this function call, I can then return back to 400549. Then you keep running, basically. You keep running until you're done. Over here, when you're done at 400557, right? What would happen is I call return. What happened on return is you first pop, then jump to here, which is 400549. So that's what happened when you return. And you update the stack pointer. All right. Any question here? Any question here? Because I feel like that's where we should stop today. Next, in the next class, we'll then talk about how does it manage the input, how does it manage the output, and if we have more time, we'll then move on to the last topic we are learning in this class, which is caching and virtual memory. All right. So again, this is where we're gonna pause today. In the next class, we'll finish the function call by talking about how does it manage the data you're passing in, like int, add, A and B, right? How does it actually communicate where's A, where's B? And then how does it manage the local data? Anything you do malloc, right? In class already on Canvas, but we want to push it because we haven't finished assembly. There's quite a bit of the content, like probably around, I would say 20 minutes of the more lecture. So assignment 4 will be out tonight. We have the between class exercise, but I'm gonna push the deadline for this by 1 week because we are a little bit delayed here. So it's due next Thursday. Wait, no. Yeah, it should due next Thursday. Basically, you start doing it on this Thursday and it due next Thursday. All right. When is A4 due? I need to decide on that because I'm trying to decide between A4 and A5. Should I get rid of some content? Because this semester there's 5 assignments, not 4. We used to have a much longer A2 that combines A2 and A3. This time I make A3 a little bit longer So you have A2 and A3 that are separate assignments, and A4, which used to be A3 in the previous semester. I can make it shorter so that A4 is only maybe like 10 days long, and then the rest of the time is for A5, which includes up to the final day, include the final exam, which I think the 21st. So that's A5, right? So we can go, and I can make it due like 23rd of the July, right? So that will basically allow you a lot more time to work on A5, and you can kind of manage your time accordingly. And then A4, I am thinking about 10 days kind of thing, and I can make it shorter. All right. Any other questions? Because otherwise, thank you so much for today. When is in class due next Thursday? When will this lecture be posted? Hopefully, around maybe 5 o'clock today. It will be done processing on WebEx. I will download that and put it on YouTube. So hopefully by maybe 7 o'clock today, it should be up. But if it's not up, please send me a reminder so I can download and post it. All right. Any other questions? Again, don't forget for the time for the makeup class here. We have extension for A3 due Friday. If you submit on time today, you get 10% extra credit. A4 will be posted tonight. We are not going to delay the deadline. The clock starts ticking tonight, basically for the. Sure, sure. Sure. I have a meeting at 4, but I'll be back on Discord at 4:30. Is that okay? All right, awesome. So I'm gonna be back on Discord at 4:30, maybe for 20 minutes until 4:50. Uh, there's no in class due today. There's no in class due today. So if the in class somehow has the due date today, that was my mistake. It's due next Thursday. Is it? Did I make any mistakes here? Yeah, thank you so much. If you need to rush to the next class, feel free to do so. And thank you for today, and we will see each other on Thursday. I just update the due date for the in-class. It should be July 7th. All right, thank you so much, and enjoy the rest of the day. See you on Thursday. All right.